In this example problem, we're going to do a chi-square hypothesis test for the sake of familiarity with what's expected. An easy way to comprehend this is to take a coin. If you have a coin, you expect in the long run that you have a 50-50 chance of getting heads or tails, and therefore your expected count of heads and your expected count of tails should be half of the amount of times that you flipped the coin. You should have a 50-50 split between the two if the coin is fair. So that's what we have here. Somebody must have been incredibly bored and they decided that they're going to spin a penny on a hard flat surface to see which side it shows up on. They did this a whole bunch of times and they came up with 38 times it landed on heads and 26 times it landed on tails. Well, we got to start this out by figuring out what is our size. How many times did this coin get spun on this hard flat surface? So 38 plus 26, find the sum of those two numbers, and that is 64. We have 64 times that we spun this coin. And I'll pull this up a little bit right now. Because a coin has an equal chance of landing on heads or landing on tails, your expected count of your two possible outcomes should be exactly half of your sample size. So for us, if we spun it 64 times, 64 times, let's say 50%, means that we should have gotten 32 heads, and 64 times 50% one more time means that we should have got 32 tails. So that's not what happened. We had much more of our outcomes come up as heads versus tails. Is that just random probability, small sample size, or is there a bias here? Is this coin, for one reason or another, more likely to land on heads than it is on tails? Well, let's do a hypothesis test to see this. So we're going to perform a chi-square hypothesis test to determine if this coin is biased. And to do so, like all hypothesis tests, we're going to have to state our null and alternate hypothesis. Well, the null hypothesis is the accepted standard, the norm. And in this case, the norm for a coin, as everybody knows, is it should come up heads half the time and tails half the time. So your probability of any one outcome should be equal to 0.50. If we are trying to judge whether this coin is biased to land on heads more than it is on tails, well, then the probability of either outcome, in this case, would not be equal to 50% or 0.50. So this is the setup that we're going to have for our chi-square hypothesis test. We need to go through now and figure out what our chi-square statistic is. So in requirement 3 down here, we are going to start by finding the component for the two possible intersections that we have. Since we only have one variable right here, heads or tails, we're only going to have two components, the intersection of count in heads and the intersection of count in tails. So let's go and start with the heads component. This is equal to, in parentheses, the observed amount of times that this spun coin landed on heads, which we have here as 38, minus the times that we would expect it to land on heads, which we determined to be 32. We're going to square that difference, and then we're going to divide by our expected amount, which is once again 32. We come up with 1.125. And the squared difference between our observed and our expected amount is 1.125 times our amount of our expected amount. Let's do the same thing for the tails components, and it's the same math. What was the observed amount of times that we had the coin land on tails was 26. In those parentheses, subtract out the expected amount of tails you would believe you're going to have, which is 32. Square that difference and divide by your expected amount of 32. So your formula should look a little something like that down here. It comes out to 1.125, and then to find our chi-square statistic, we just sum up all those numbers, and we come up with 2.25. So the purpose of this is we can use it to establish some form of probability. In requirement 5, we're going to do it via a table, and the table provided over here on the side has a bunch of intersections. We are going to know what our degrees of freedom are. And I gave it to you in the problem in here. The degrees of freedom for this test is 1, but how did I determine that? So the degrees of freedom is found in all of these things as the number of different variables that you had minus ones. So we only have one pair over here. We have two possible outcomes. 2 minus 1 is 1. I need to go into the row where degrees of freedom are 1 and go over until I find a number that is reasonably close right here to the closest thing I can find to our chi-squared statistic. So I go over and I have degrees of freedom of 1. I'm looking for the number that's closest to 2.25, and it's looking like it's about this number right here. So we can say approximately that our chi-squared statistic, which is not what I want to have here, probability, excuse me, is 0.10. That's not the most scientific way to do things. So let's find the exact probability, our exact p-value. And we can do that in Excel using the chi-squared dot distribution dot right tail function. So I'm going to say this is equal to chi-squared, which they abbreviate to CHISQ, dot dist for distribution, dot rt for right tail. I open a parenthesis and it's going to want two inputs, x and degrees of freedom, or x is our statistic. So I'm going to click on that 2.25, comma, our degrees of freedom, which we just determined and was given up here as 1. And when I put that in, I come up with 0.134. So what does this imply? This is the probability that if you state that the alternate hypothesis is true, you reject the null hypothesis for the alternate hypothesis, it is the probability that in the long run, once you get more information, once we spin this coin more than 64 times, that we're going to be wrong. So we have a 13.4% chance that we're going to claim that this coin is biased and the probability of landing on each side is not equal to 50%, get more data and find out that we made an errant claim. And you give yourself a level of comfort that you call it your significance level. And for us, our significance level is 5%. So we're only comfortable making this claim if there's less than a 5% chance of error. Well, we don't have less than a 5% chance of error. We have a 13.4% chance of error, if you will. So do we have statistical evidence in this case that there is a bias to this coin? No, we do not. We fail to reject the null hypothesis that this coin is fair and unbiased because we do not have significant evidence to prove that it is more likely to land on heads or tails than any other coin.